All right, y'all, so we're going to start by reviewing some of those big ideas from orbital notation and getting a little practice with those as well. And you can see, right, like as you're drawing all these lines and drawing all these arrows, scientists eventually kind of got tired of drawing all of that out and they wanted to look for a better way. So after we review, we're going to look at something called electron configuration, which is a shorter way to write out orbital notations. So let's start with a little bit of review. So here are some key reminders about our quantum numbers. So the first was our principal quantum number, right? It was giving us our distance from the nucleus, which we described by energy levels. And then for its values, right? So right here, the values were going to be 1 through 7 as our potential. All right, then we had the orbital quantum number, and that was describing like the shape of the way the electrons were moving. And we had 4 different potential shapes that we could look at, right? So our different variables, we have S, P, D, and F. And then we had the magnetic quantum number, and that was telling us like what it looks like in 3D, right? So we were talking about like your x-axis, your y-axis, your z-axis. What do those shapes look like, right? So a sphere looks the same no matter what. A dumbbell, X, Y, Z, 3 different orientations. Okay, so our values when we are talking about the magnetic quantum number, that was that S has 1 orientation, P has 3 orientations, D has 5 orientations, and F had 7. So let's review those again. Okay, so then we need to keep in mind our rules that guide us for orbital notation. That first rule was Aufbau. Okay, so Aufbau said that electrons are going to fill the lowest energy level before moving up. So energy level 1, then 2, then 3, and so forth. Pauli exclusion principle said that no 2 electrons can be in the same place at the same time. That was part 1. Part 2 is that electrons in the same orientation must have opposite spins. And so that was like when we do the up arrow and then the down arrow, that is our way of indicating opposite spins. And then the last was Hund's rule, and that was that electrons fill each orientation of a sublevel before pairing up. It is key that you note it is each orientation of a sublevel, not each orientation of an energy level. So like you would do for P, you would do up, 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 then down, 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 before moving on to S, before moving on to D, whatever it might be. Okay, so you fill that orientation, each orientation before they pair up. Okay, and then the next thing we talked about was how we can actually follow the periodic table to do this. So if you recall, for our periodic table, we can look at it in sections where this is S, this part is P, right here in the middle is D, and then down here at the bottom, that is our F sublevel. And you'll always have periodic tables for quizzes and tests, so you can always just write that right on there. Like make yourself your own little cheat sheet, right? And then our energy levels are on the side. 1, 2, 3, 4, 5, 6, 7. Okay, they follow the rows. But then there was that super, super annoying feature, the fact that this, even though it's in the 4th row, is actually 3. This is 4, 5, and 6. Okay, so even though it's in the 4th row, this is 3D. Even though this is in the 5th row, this is 4D. And again, it's beyond the scope of this class. Don't worry about it. Just trust me. Okay, just go with it. So when we are filling electrons, we follow that that path, right, of the periodic table. So we would do 1s, 2, 2s, 1, 2, 2p, 1, 2, 3, 4, 5, 6, 3s, 1, 2. 3p, 1, 2, 3, 4, 5, 6. 4s, 1, 2. 3d, 10. 4p, 6. 5s, 2. 4d, 10. 5p, 6. Okay, so that is that piece, right? You follow the periodic table when you are filling it in. And so this is just a good thing to always have in mind. With this, I want to put some input into when you know how to stop. Okay, so remember that for a neutral atom, the number of protons and the number of electrons are the same, right? So with that in mind, if that has to be true, then if we know the atomic number, right? So if I told you element fluorine, then we know that fluorine has an atomic number of 9. Therefore, it has 9 protons. Therefore, if it's neutral, it has 9 electrons. Okay, so for a neutral atom, the atomic number is going to correspond with the number of electrons. A little bit later, we're going to get into what happens when those change, when they're not neutral, because we know that they can have charges, ions, right? We know that word. Neutral, number of protons equals the number of electrons. And then a last little reminder here, okay, is about how these things like fill. Remember that, you know, these labels, right, your labels, okay, are going to be the energy level and the sublevel. Okay, and then the number of lines, 1 versus 3 versus 5. Okay, the number of lines, it equals the number of orientations. Right, so S would have 1, P would have 3, D has 5. F has 7, but we're not going to deal with it, but, you know, whatever. Okay, so when you are doing this thing, that is how your drawing needs to go. So let's say we were doing chromium. All right, so we find chromium on the periodic table. Chromium symbol is Cr. Sorry, this periodic table is not fitting. Hold on. There we go. Okay, so chromium symbol is Cr. So it's element number 24. Therefore, because it's element 24, that means it has 24 protons. Because it's neutral, 24 electrons. All right, so with our periodic table next to us, I'm going to look and do chromium. So we said, right, so it's going to go 1s2. So I'm going to come over here, 1s1, 2. 2s, 1, 2. 1, 2. 2p, 1, 2, 3, 4, 5, 6. Remember Hund's rule, we're always going to do our up arrows first and then come back and add our second. End of the row, ding. 3s, 1, 2. 3p, 1, 2, 3, 4, 5, 6. Up, 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 down, down, down. I'm at argon, right? So, and then I go ding, 4s, 1, 2. Okay. Then 3D, again, we said it was going to be 4. 1, 2, 3, 4. Hund's rule. 1, 2, 3, 4. So again, the total number, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. The atomic number was the number of protons, therefore the number of electrons, therefore how many arrows I needed to have here. Orbital notation for copper. Go ahead and fill that in. So again, it was the element copper, which is Cu, which when you find it on the periodic table is element number 29. Okay, so you should have had 29 electrons. All right, so now let's talk about ions. So if you recall from when we were talking about isotopes, ions are elements that have a charge. So when there is an uneven number of protons to electrons, that is a ion. Okay, so again, when there's an uneven, or unequal is a better word, an unequal amount of protons and electrons. If something has a positive charge, then you would subtract that to figure out how many electrons there are. If something has a negative charge, then you would add whatever that number is to figure out how many electrons you had. So if something has a -1 charge, that means there's one more electron. If something has a +1 charge, that means there's one less electron. Okay, so here on the left, this is the normal orbital notation for oxygen, okay? Oxygen is element 8 on the periodic table, okay? So when we look at it, 1s, 2, 2s with 2, 2p, 1, 2, 3, 4. Okay, so my drawing, 1s with 2, 2s with 2, 2p, 1, 2, 3, 4. Now I'm telling you that that oxygen has a -2 charge. So that is telling me that there are 2 more electrons. So normal oxygen, 8 electrons. Oxygen with a -2 charge is 8 electrons plus 2 more. So you'll do the regular one first, which you can see is using the black arrows. And then when there was the -2 charge, we add 2 more electrons to that atom. So that is what ions look like. So for example, potassium ion. Potassium is element 4s. So I will have to tell you what these charges are. So potassium ion is going to be +1. And so that means that there is 1 less electron. So we would have 1s, 2, 2s, 1, 2, 1, 2, 3, 2p, 1, 2, 3, 4, 5, 6, 3s, 1, 2, 1, 2, 3, 3p, 1, 2, 3, 4, 5, 6, 4s, 1. And then what happens is, because we lost 1 electron, boop, gone. Okay, so now what I want you to do is think about sulfur. I'm going to tell you that sulfur has a -2 charge. Okay, so it's sulfur with a -2. Okay, so this is sulfur with a -2 charge. Just to walk you back through the last part of that though, regular sulfur would have looked like that. Then, because it has a -2 charge, that's telling me that it has 2 more electrons than it normally would. So then I add in those last 2 and fill the row. All right, so like I said, scientists got exhausted writing these things out all the time. They're like, forget it, I don't want to do this anymore. So they wanted to come and make a shorter version. So you might have noticed that as I was like talking through how these things fill, I was saying like 1s, 2, 2s, 1, 2, 2p, 6. Scientists were like, okay, let's just write it like that instead of doing it out. So we still say 1 for the energy level, s for the sublevel. And then instead of drawing these arrows and these lines, they just simply are going to list how many electrons are there. Okay, so it's much easier than doing our orbital notation. So quick reminders here. Take a second to read this and fill it in, please. Okay, so hopefully you remember S holds 2, P can hold 6, D can hold 10, F can hold 14. Hopefully that's easy to remember. All right, so orbital notation versus electron configuration. So let's say we were talking about nitrogen, for example. Nitrogen is element number 7. So it's going to have 7 protons or electrons. So filling in nitrogen, 1s, 2, 2s, 2, 2p, 1, 2, 3. So the orbital notation, 1s with 2, 2s with 2, 2p with 1, 2, 3. Okay. Same way I was saying that out loud to figure out how to write it, 1s with 2, 2s with 2, 2p with 3. Okay, so you kind of like what you're saying out loud to try to figure out like how you're drawing your orbital notation is what you should write down for the electron configuration. So again, following that periodic table is going to be helpful for doing this. So it was like 1s, 2, 2s, 1, 2, 2p, 1, 2, 3. Okay, that what I was saying, that is the electron configuration. So our next example here, we have fluorine. All right, so let's look at the periodic table. Fluorine is element 9. 1s with 2. 2s, 1, 2. 2p, 1, 2, 3, 4, 5. Okay, so what I said out loud was 1s, 2. 2s, 2. 2p, 5. Right, calcium. Here it is. 1s, 1, 2. 2s, 1, 2. 2p, 1, 2, 3, 4, 5, 6. 3s, 1, 2. 3p, 1, 2, 3, 4, 5, 6. 4s, 1, 2. Again, that was 1s, 2. 2s, 2. 2p, 6. 3s, 2. 3p, 6. 4s, 2. Go ahead and do arsenic. All right, so there is arsenic for you. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3, right? So that last row, 4s, 1, 2, oh, sorry. 4s, 1, 2, 3d, right? Super annoying, 3d after 4s, 3d10, 4p, 1, 2, 3. Okay. Couple more practice for you, so give those a go, and then when you're ready, you can take a look at the answers.